Have you ever just looked at the world and wondered how we can possibly understand something that's, well, massively, overwhelmingly complex? Not just complicated, but something with a zillion moving parts. How do we find simple, predictable rules in a world that so often feels like pure random chaos? Well, that's exactly the challenge at the heart of a field called statistical mechanics. I mean, really think about that question. We're not talking about a few billiard balls on a table where you can calculate all the angles. We're talking about systems with an absolutely astronomical number of parts, all doing their own thing. You just can't track every single water molecule to figure out exactly when a block of ice will melt. And you definitely can't follow every single data packet to understand traffic on the internet. The sheer scale makes it completely, utterly impossible. So, how in the world do scientists get around this? Well, they use this incredibly clever, powerful conceptual tool. You can think of it as a kind of statistician's trick, and it completely changes the game. It's a way to take what seems like unknowable chaos and turn it into something with beautiful, predictable clarity. And here is that trick. It's a concept called the ensemble. The big idea is this. Instead of trying to predict the outcome of one specific chaotic system, you step back. You study the statistical behavior of a huge collection, an ensemble, of all the possible outcomes. It's a total shift in perspective. And this visualizes the power of that idea perfectly. On the left, you've got a single random walk. Think of it like one molecule bouncing around in a gas. Its path is jagged, totally unpredictable, you have no idea where it's going to end up. But on the right, that's where the magic happens. We're looking at the endpoints of thousands of these random walks, all put together. And boom, a simple, elegant, predictable pattern emerges. That circle is the hidden law governing all that chaos, and you can only see it when you look at the whole collection. Now, this powerful idea of the ensemble, it's not just for physics, not at all. It can be applied pretty much everywhere, and it helps us solve some surprisingly common and often really counterintuitive real-world problems. So, to see this in action, let's take a classic puzzle, one that actually appears as an exercise in the source material, the birthday problem. It seems simple on the surface, but it's a perfect example of this kind of ensemble thinking. So, what's the answer? It turns out you only need 23 kids in a room to have a 50-50 shot that 2 of them share a birthday. That just feels wrong, right? Our intuition screams that the number should be way higher, but it's true. And the solution comes from analyzing the ensemble of all possible birthday combinations, which shows that the odds of a match climb way faster than we think. This same way of thinking about collections and connections and probabilities, well, it leads us to another very famous number. 6, as in 6 degrees of separation. Yeah, this isn't just a party game. It's a really deep insight that comes from studying networks, which is another huge area where statistical mechanics is applied. The small world model helps explain how our massive global society can feel so surprisingly, well, small and connected. And here's basically how you build one of these models. It's surprisingly simple. First, you imagine a world where everyone just knows their immediate neighbors. Very local, very orderly. Then you just add a tiny number of random long-distance links, the shortcuts, like a friend you made on vacation. And this is the mind-blowing part. Those few shortcuts don't just help the 2 people they connect, they fundamentally change the entire network. They dramatically slash the average number of steps it takes to get from any one person to any other person on the whole grid. A tiny random change creates this huge, system-wide effect. Okay, so this leads us to an even deeper, even cooler concept, emergence. What happens when the collective behavior of all these individual parts doesn't just average out, but actually creates entirely new states of being, new realities with their own rules that just emerge from the crowd? This quote describes a system right at a tipping point. It's a phenomenon called a phase transition. The model here shows a magnet right at its critical temperature. A little colder, and all the tiny atomic magnets align. They form one phase, a magnet. A little hotter, and they're all just random. A totally different phase, a non-magnet. But right on that razor's edge, it's as if the whole system is deciding which collective state it wants to fall into. And this concept of phases goes way, way beyond just ice, water, and steam. It describes the weird behavior of superfluids, the difference between an earthquake fault that's stuck and one that's sliding, the incredible flocking of birds, and even, believe it or not, different possible states of the vacuum of empty space right after the Big Bang. Each one is a new reality, born from the interactions of countless tiny parts.
So, when you put it all together, this way of thinking, of analyzing the collective instead of the individual, it gives us this powerful and universal toolkit for making sense of complexity, everywhere from the tiniest computer chips to the vastness of the cosmos.
And just look at the sheer breadth of its reach. These examples are pulled right from the problem sets in the source material. We're talking about optimizing computer algorithms, understanding social networks, engineering for reliability by predicting which part in a system will fail first, all the way to modeling the birth of stars and the echoes of the Big Bang. It's amazing. It's the same core set of ideas at work everywhere.
So the ultimate takeaway is this. Statistical mechanics teaches us that simple, elegant, and powerful new laws can emerge from the noisy chaos of countless individual interactions. And it kind of makes you wonder, doesn't it? What unseen rules are governing the complex systems in our own lives, from our economies to our ecosystems, just waiting for us to discover them, if we only learn to see the crowd, instead of just the individual?